Today, we're diving into a question that affects pretty much everything around us, from our phones to the bridges we drive across every day. How do we really know when something is about to break? And what if AI could give us a heads up just in the nick of time?
Seriously, just think about that for a second. A massive bridge, a jet engine spinning at incredible speeds, or even the complex little device in your hand right now. What if you could know, with pinpoint accuracy, the exact moment a critical piece was about to fail?
You know, for the people who build our world, this is so much more than a cool idea. Getting this right is literally the line between a routine fix and a catastrophic disaster. For decades, this has been the holy grail. But our traditional methods, well, they've kind of hit a wall. Okay, so here's how we're going to break it all down. First, we'll talk about the fundamental challenge of why things break. Then we'll get into AI's incredible predictive power and see it in action in the lab. From there, we'll scale up to entire systems, look at the roadblocks we still face, and finally, peek into the future of materials. Let's jump in. So let's start with the core problem. Predicting when something's going to break is just monumentally complex. It's not as simple as asking, how hard did you push it? No, it's this incredibly complicated dance between a material's hidden chemistry, tiny invisible cracks, the heat, the cold, all of these things interacting in ways that are just about impossible for us to track. So, how in the world do you solve a problem that messy? Well, this is where artificial intelligence steps onto the scene, and it is a total game changer. It's giving us a brand new playbook for understanding that age-old battle between stress and strength. The magic behind all this is something called predictive modeling. The idea is pretty brilliant. You feed an AI just massive, and I mean massive amounts of data. We're talking everything from a metal's chemical recipe to the humid, salty air it lives in. And then you just let the AI go to work, hunting for all the hidden patterns that tell the secret story of how and when it's going to fail. And the process, when you boil it down, is actually pretty straightforward. Step 1, you pour in all the data you can get your hands on. Step 2, the AI algorithm just sifts through everything, connecting dots and finding these complex relationships that a human engineer might never, ever spot. And finally, step 3, it gives you an incredibly precise prediction of that material's breaking point. Okay, so that's the theory, but does it actually work in the real world? Well, let's see what happens when the rubber meets the road. Because researchers are putting this to the test in labs right now, and the results, they're pretty mind-blowing. Just take a look at this recent work by Zhu and his team. They're not just predicting failure, they're using AI to design better materials from the ground up. Their AI can dream up a new metal alloy that's perfectly optimized for both strength and resistance to something nasty called stress corrosion cracking. That's a huge cause of failure, where a material just gives up under stress in a corrosive environment. And get this, the AI can even spot the microscopic cracks right as they're born. And it's not just for exotic alloys. Other research is using AI to quickly figure out how strong a structural beam is without having to do a bunch of expensive physical tests, or even to fine-tune the settings on a 3D printer to make parts that are way stronger and more reliable. And this quote really gets to the heart of AI's superpower here. It can look at the microscopic level at all the tiny fibers and particles reinforcing a material and understand how they all work together to create this overall strength. It's this hidden teamwork, this synergy that was basically invisible to us before. Now, so far, we've mostly been talking about a single part or a single material. But what happens when you take that and build an entire airplane or a city's power grid out of thousands of these interacting parts? Well, the complexity just goes off the charts. And this is a huge leap in difficulty. I mean, predicting when one gear might fail, that's one thing. But predicting what happens in a system of hundreds of gears all working together, now you've got to worry about cascading failures. That terrifying domino effect where one small break triggers another and another until the whole system comes crashing down. Our old models just can't keep up with that. But this is exactly where AI shines. It has the raw horsepower to analyze all of those tangled, interconnected relationships at the same time. By pairing it with some really advanced statistical tools, we can finally start to model these complex systems and get a real, holistic prediction of how the entire structure is going to act under pressure. But of course, this isn't some magic wand we can just wave over every problem. Not yet, anyway. Like any groundbreaking technology, there are still some pretty big hurdles to clear before this is a standard part of every engineer's toolkit. When you look at the research, 3 main challenges really stand out. Number 1, and it's a big one, is data scarcity.
AI models are hungry for data, and for a lot of materials, we just don't have enough comprehensive, high-quality data to train them properly. Then there are gaps in our ability to model really complex forces and some statistical gaps for handling certain kinds of data.
And to get a little more specific, an AI model that's an expert on one type of steel can't just be applied to aluminum. It doesn't transfer well. Most models are also much better at predicting failure from a single big force rather than the slow, repetitive stress that causes metal fatigue over years. On top of that, we're still working on developing the right statistical tools for the job.
So, keeping those challenges in mind, what's next? Where do we go from here? Well, the path forward is actually becoming surprisingly clear, and it's really exciting.
And here it is. This might be the single most important takeaway from all of this. The future is not about choosing between AI and our classic understanding of physics. No. The future is AI times physics, working together to create something way more powerful than either one could be on its own.
The next great leap forward is all about creating these hybrid models. Imagine combining the incredible, almost intuitive pattern-finding ability of AI with the solid, time-tested foundational laws of physics that we know are true. You get the best of both worlds. AI's power to see connections we can't, all grounded in the fundamental principles of how the world actually works.
Which leaves us with this one last, huge question to think about. If we can really pull this off, if we can successfully merge the deep insights of AI with the undeniable laws of physics, could we be heading toward a future where things are designed so well and monitored so closely that unexpected, catastrophic failure just becomes a thing of the past? It's a bold thought, for sure, but it's one that's slowly moving out of science fiction and into the realm of real possibility.